Another place where linear models are used is in economics. We talk about supply and demand. The supply is how many of a certain commodity, let's say cell phones, how many are available to be bought, how many are being manufactured, and demand is how many people want to buy. Now, typically, when you raise the price, that stimulates people to manufacture more phones. Okay, so there'll be more phones available. So more will be manufactured. But if you raise the price, fewer people are going to want to buy them, so fewer are going to be bought or sold. Okay, I use bought because I don't want to get another S term, because what we call the number manufactured is supply. And what the number that are to be bought is what we call the demand. So what we have here is a graph where we have the price. Okay, supply could go on this axis, or demand. This is just a number, and the supply is a number, the demand is a number. Demand is how many we expect to be sold, supply is how many we expect to be manufactured. So as the price goes up, the supply goes up. So we have the S function, the supply function. Now, in reality, the supply function is not a straight line, but a straight line model is still very useful as a first approximation and to understand how supply and demand interact. So we're going to do that. Now the demand curve is going to be decreasing, greater price, less demand. So we have some demand function that we'll call D. Now I've just drawn these straight lines without regard to where they stop or start. Presumably there aren't going to be any negative prices, so we want to limit the domains of these functions to actual possible prices. Also, the demand function is clearly not very linear, not completely linear, because if the price drops to zero, the demand is going to go up very rapidly. You're going to probably have something very much like a vertical asymptote at this point. It's not going to remain linear. Still, we assume the linear graph, and maybe we restrict the domain to some part of the positive price axis. So maybe we just start the domain here and end it here. We're not going to get into that. We're just going to say, okay, we got a supply, we got a demand. Now, this point where the two linear functions meet here is called the equilibrium point. Okay, this is equilibrium. Where the supply equals the demand. So if you're at the equilibrium point, there's usually not a lot of impetus to move in one direction, to move the price in one direction or not, but there might be. And you know, I'm not an economist, and I'm not going to get into too much interpretation of this situation, but you have this equilibrium point. And in subsequent courses, should you go to an applied calculus course, you have things like producer surplus, you have elasticity of demand, you have concepts like that that are calculus-related concepts that require that you understand this basic supply-demand relationship so that you can build on it, which is one of the reasons in a college algebra course, which often precedes an applied calculus course, why we do a lot of economic models, because they're very common in those courses. Those courses are generally for business, social sciences, and the biological sciences. Okay, so let's say that the supply function is 500 plus 40p. That would mean that you have a y-intercept of 500 and a slope of 40. A positive slope, there's your 500. And the demand is 5,000, which would be the number you would expect to be demanded if the price was 0. I think the number would go up a lot higher, but I mentioned that before. We'll stick with the linear model. And the slope of -20. That would be -20 units sold for every, say, dollar increase. I haven't put units on these, but keeping it as simple as possible for the first example here. Okay, now my question is, what is the equilibrium price and how many sold at that price? Well, we can see in the graph that there's a point where a function that's increasing and starting at a lower value will have to meet a function that's decreasing and starting at a higher value. How do we algebraically find that? Equilibrium is where the number sold equals the number demanded. So, in terms of the graph, here's your equilibrium price. And here's the number sold equals the number demanded. So how do we find that point when we're given these two functions? Well, we just set S equal to D. S is 500 plus 40p, and D is 5,000 minus 20p. And what do we have? We have a linear equation. Not only that, but it's a linear equation that's quite easy to solve. No fractions, no decimals, nothing tricky. We simply add 20p to both sides, which will give us 60p over here. We subtract 500 from both sides, which gives us 4,500 over here. And we find that the price is 4,500 over 60, which is 75. Presumably, that would be our selling price, let's say $75. So, by setting the two equations equal and solving them, let's just assume that the price is in dollars, so that's 75. Now, what's the number sold or the number demanded? Well, we plug this price back into the function. Let's say the number sold equals 500 plus 40p. We plug this price in for p, and we get 500 plus 40 times 75, and 40 times 75 is 3,000, so that's 3,500. So that equals 3,500. Now, we calculated the number, and I said the number sold. S is not the number sold. S is the supply. The supply, the number available, will be 3,500. If we plug 75 in for the demand, we'll get 5,000 minus 20p. If p is 75, 20 times 75. Well, you should do this. You should pause before I say this, or after. You should verify this in any case. 20 times 75 is 1,500. If we subtract 1,500 from 5,000, we again get 3,500. You should verify this. If you've solved these equations correctly, then this number will have to equal this number when this number is substituted for p. Our final conclusion is that the equilibrium point is 75, 3,500, equilibrium point for the supply and demand.